Yeah, so we find ourselves with this pre-Earth, if you like, which is predominantly slush. Over the course of billions of years, the heavier elements are going to reach the outside of the sphere. So those elements are going to form the crust and also the mantle, and then lighter liquid elements such as the water and ice are going to migrate inwards. So for us ever to warm up, because as you go down through the crust, it is warmer. So there has to be a mechanism for the warming of our planet, and that basically is done by the breakdown of uranium and thorium in the mantle, which creates heat. That heat in turn is going to warm up our icy core, and over the period of time, that ice and frozen elements of other gases are going to thaw. So then we get to the point where we've got a liquid core, but it's still being heated. So as it continues to be heated, it's going to come to the boil. And when water comes to the boil, you get steam. Steam in turn can exert enormous amounts of pressure. And as more and more steam is created by the heating of the inner core, the pressure becomes that much that it forces cracks in the surface of that crust. Those cracks then will vent magma, and they'll also vent steam. So you get the situation where the Earth is splitting along its continental margins and being vented, but not vented enough to stay a constant size. The pressure is such that the continents are then prized apart along the weakest link between them, and then you get what we now see as mid-oceanic growth of the new crust,
yeah,
which is formed from basalt and volcanic activity. And as Maxwell and Adams have shown,
Maxwell and Adams, yeah,
they show the continents being pushed apart by this new crust, which is being formed along lines, as everybody knows, between Africa and South America. You can see that those two continents did fit together.
Yeah, at one time, yeah.
And what the graphics that they've done, which are fantastic, they've shown this from every angle of the planet. Yeah. They show quite clearly that there's no subduction, and that this new seabed is young, and it's less than 200 million years old. And so there's the direct evidence from the sonar work done by the US, I believe, in the 60s, and we are now at the point where we can explain the mechanism of why these continents are being pushed apart, and I call it steam-powered Earth expansion. Evidence of this phenomena can be seen all over the solar system, on planets, our moon, other moons, and I think the time has come for this to be established as fact. So we have the mechanism now for Earth's expansion, and we also have the explanation of why for the first 4 billion years of Earth's history there was no expansion. There was no expansion because the inner core of our planet was just frozen stiff, and until it transformed from ice to water and then to steam, there was no mechanism for it to expand. But expand it has, and it's expanded exponentially. The heat is generated as just turning a vast reservoir of water into steam, and that steam is irresistible in its expansion.
And then, of course, the other point which I was impressed with when I thought about what you'd put on the table here is, because one of the big mysteries in all of this, one of the big Earth mysteries, is where the oceans came from, isn't it?
Yeah.
So essentially we've essentially got the answer to that, haven't we?
Yeah. I've done some maths on this, and I've calculated that probably all the oceans, the water in all the oceans, is little more than 1 or 2% of what was once subterranean, if you like.
Yeah.
And that the oceans that we have now, that water has been forced through these cracks in the mid-ocean ridges, and that's the source of the water, or the vast majority of the water on our planet. I believe that there was water, surface water, but there were only shallow seas, as most people who are familiar with this subject will say.
Yeah,
there were
right.
shallow seas, and that's where all these fossils are found, in the remnants of these shallow seas that might be miles up in the Alps or wherever they find these fossils. But there were once shallow seas, and that's where a lot of the early development of life went on, up until and including the dinosaurs.
Yeah. And so, I mean, we've got a couple of answers to some of the fundamental questions in the Earth's formation, and because a lot of people have said that the oceans probably came from comets crashing into the Earth over millions of years, and that doesn't really fly too well, really, does it? Because of the amount of comets that you'd need to fill up the oceans would be probably fairly substantial, and and I don't think that's certainly not regarded as the absolute answer to the mystery of the formation of the oceans, is it?
I've never considered that.
No, neither have I. But I think on that subject, when we're discussing this, and whether, for example, there might be things that might trigger this outflow of water. I think if we've, taking what you said, one thing that I suggested to you, I mean, we've only just discussed this in passing, really. We haven't really gone into great lengths to analyse it all. But is this idea perhaps that if we've got this expanding, boiling kind of chamber inside the Earth, where the steam is coming out, what would happen if we had a large asteroid or cometary impact, coming in and affecting the mantle? Yeah,
I mean, we can't prove it, but it could stimulate by if it hit in a vulnerable area. It could stimulate a great outflow of both magma and water from the inner core. So you could have had a sudden deluge, in theory, and that could have been, the flood. Many cultures talk of a flood completely engulfing the planet.
Yeah.
Well, if you look at Maxwell's and Adams' description of the formation of mountains, it's to do with the changing shape or radius of the Earth. So if you can imagine back on the pre-Earth, there wouldn't have been mountains. The continents would have been probably undulating with a few shallow seas, but not have the great height of the mountains. So the volume of water that we have on the surface now could easily have covered all the continents with several kilometres of water. Yeah.
So again, we've got observations here, and to explain, what's been happening with the volume of the oceans and how they've changed. So I think that's an important thing to consider, because we're not. One of the things that you pointed out, one of the fundamental things, is that we're not changing the mass from the time of the original formation of the Earth. I mean, not substantially anyway. You might have bits and pieces that accrete and so on, but that'd be a very, very tiny sort of fraction of a percent of the overall mass. Whereas these other, both Neil Adams and James Maxwell, have talked about an increase in mass.
Yeah.
And so that's again one of the fundamental things which.
This is different.
It's different, and this explains it, I think, very well. And I think one of the other things that you'd looked at, Peter, was the sort of surface area of the pre-expansion Earth, and you tried to do some calculations on that. If you'd like to describe, how you went through that process.
Yeah. Well, being unable to do the CGIs that Maxwell and Adams had done, I decided to go on the internet and find out what the surface areas of the continents are now, the area of the continental shelf, which is also part of the pre-Earth shell, if you like, and ignore everything to do with the oceanic crust. So by doing that, you get a fixed area, which is the continents now plus the continental shelves. And by doing the maths, you can come to a figure for the size of the pre-expansion Earth. Then, as it's expanded, it's been added to by the oceanic crust.
Yeah.
So I got a figure of something like 59% of the radius of today's Earth, which fits in pretty well with Maxwell and other researchers. And
so you basically went from the surface area, you said that would be obviously a spherical surface area, and then you could go using the 4/3 pi r cubed or whatever, or the pi r squared. You can then go back and work out what the radius was by using that calculation. Yeah.
So then what I did was I calculated the not the mass but the volume now of the Earth.
Yeah.
Because we're saying. I'm saying that we've got the same mass and the same volume, if you like, as we had 300 million years ago.
Yeah.
So doing the mass for today's radius of the Earth and subtracting the volume of the pre-expansion Earth, you get a figure of what is not there, if you like.
Yeah.
And pretty much that gives you a radius of what is now the gaseous part of the internal makeup of our Earth, and that has a radius of 5,900 kilometres.
Right.
So if you take that away from the actual radius of the Earth, you get a figure of 400 and something kilometres. So that is the thickness of the shell of the planet. So that's made up of the crust, the mantle, this watery element, and then the rest is gas to the centre of the Earth.
So you actually managed to quantify the extent quantify the sizes of these components within sort of certain limits.
Yeah. You can only work out the volume because we don't know what the actual ratio of solids to liquids are.
No.
It's just that area. I've done 3 different calculations, which I'll no doubt go in.
Yeah.
But there's nothing to say that any of those are right. It could be greater solids or greater water content. But the fact that there is sufficient water subterranean to produce enough gas, steam, over time, that the Earth's expansion will be exponential, as has been shown by other people.
Yeah.
And I believe that will continue until there's some kind of equilibrium reached. But I believe by that time, who knows what the planet will look like.
We don't know, but indeed, you came to the sort of same conclusion as Maxwell, didn't you? Because you were talking about the Earth ending up as something similar to some extent to a gas giant.
Yeah.
So.
And there again, it does throw water on his theory and Adams of a growing Earth, because an exponential growing Earth, it's going to gobble up all the matter in the solar system in no time at all.
Yes.
And if all the other planets are expanding, then where's it coming from?
Yeah. Yeah.
So, sorry to say, Adams and Maxwell, but you've got it wrong.
The other thing that we'd spoken about was this Jan Lamprecht, who's a South African, who'd modelled the seismic signals that had been sort of sent down through the Earth during earthquakes, and they come out the other side. And various scientists have claimed that this proves certain things about the structure of the Earth, and Jan Lamprecht has also spoken about that. So if you just tell us your thoughts on that.
Yeah. Basically, one of the first things that Jan Lamprecht says is that these seismic waves don't flow through liquid. And the first thing I would say to that is we've got a crust and under that crust we've got a fluid mantle. So my take on that is that these seismic waves are not flowing through that mantle because they would be absorbed because of its liquid state, even at temperatures and whatever. So I think all the seismic data is just recording waves that are being refracted in between the upper and lower edge of our crust.
Right.
And that I believe it's up to the seismologists to prove anything other than that, because Jan Lamprecht, he said, he found evidence that there was a hollow core to our planet.
Yeah, yeah.
So I think the ball's now in their court to dismiss what we are saying, rather than us try and prove them wrong.
So that gets us on to, I think, the topic, as I was just saying there, of essentially we're not talking about hollow Earth, before people misunderstand that.
No, what I'm suggesting is that this superheated reservoir of water, which deep below the mantle, is being and other liquids are being turned to gas. So this inner volume it's not a vacuum.
No.
It's full of high pressure, high temperature steam for the most part, and other gases, because as we've said before, I believe all the gases, or most of the gases, migrated to the centre, and that's where most of the gas is going to be.
Right. And so that then takes us on to the general sort of idea of mass distribution, isn't it? Because one of the things we didn't talk about properly before was when we were talking about the gravity changing. That's one of the big mysteries that I think you've also solved.
Yeah.
In the way, because essentially what I summarised it in that it's the mass distribution which causes a change in gravity, not a change in mass. It's just the distribution of the mass, isn't it? So if you want to tell us a bit about that.
Yeah, initially when I did the accepted formula for the attraction due to gravity, and I thought it would just come like that, and that it would be easy, but it didn't, because when I first did the calculation, as I think that Max Law has, if you take the centre of gravity of that pre-expansion Earth, be it 3,000 and odd kilometres, and then compare it with the attraction due to gravity today, you actually get a figure that is 3 times greater than it is now. So the dinosaurs required it to be a quarter of what it is now, and that threw me for a bit.
Yeah.
But eventually I realised that as you said, the distribution of that mass on the pre-expansion Earth, the centre of that, the centre of gravity, if you like. You probably do better with the maths of explaining exactly where it might have been, but I estimated it to be 600 to 1,000 kilometres deep. Yeah. So then so taking that as being the R in the R squared bit of the calculation, you end up with a figure of between, well, let's just take the higher figure of 1 million. Yeah.
Right.
So you're dividing the sum of the two masses and the gravity constant. You're dividing it by 1 million.
Yeah.
When you come to our Earth as it is now, most of the mass is concentrated in less than 500 kilometres. So the centre of that might only be 400, 500 at most. So when you square that, you get a figure of 250,000. So that is a quarter of the distance that we had in the pre-expansion Earth.
Right. Which
exactly equates to the dinosaurs living on a world that had a quarter of the gravity that we have now.
Yeah, yeah.
And that just sort of gave me the pat on the back, if you like, saying, yeah, you are right in what you're thinking.
Yeah, well, I mean, that again, backs up the constant mass sort of scenario rather than the increasing mass. Yeah. Because and then the other thing we didn't talk about, we should have talked about, because that's just reminded me, is the issue of the core, because it's assumed that the Earth has an iron core, doesn't it? And tell us about that.
Right. Yeah. That I more or less dismissed that as soon as I saw the NASA thing with the heavier elements going to the outside. But obviously, it's in all the textbooks, so you've got to. The reason why it finds itself in the textbooks is because somebody's assumed that something metal down there is creating a magnetic field, which is keeping life possible on the planet. But as we've discussed, there's a lot of new thinking going on in astronomy, and one of the new threads of thought is the electric universe, and the fact that all the suns and the galaxies and planets are connected electrically. And this is easily shown to be true of the relationship between the sun and the earth, that we're electrically connected. So the earth is spinning, it's in an electric current or an electric field, and I think that's all you need to generate the magnetic field is the rotation of the earth, which is the crust and the mantle have got high proportions of metal of iron, and I don't think you need an iron core. In fact, we haven't got an iron core, and that's that explanation really, as best I can do.
Yeah, I mean that I agree with you, because as you say, the only reason why they need an iron core is to explain the Earth's magnetic field. But as we would now contend, if you've got a kind of partly external reason for the Earth's magnetic field, which is this electrical interaction between the sun and all the other planets, and indeed even sort of going beyond that into the sort of nearest star cluster and that sort of thing, you can extend it to that. Then we don't, as I say, we don't need the. I mean, no one's ever seen the iron core. Nobody's ever drilled down that far. It's just assumed to be there purely to explain the magnetic field, and then that's the same with the needed expanding mass for the expanding Earth under Maxwell and Neil Adams. They need the expanding mass to explain the change in gravity, whereas what you've proposed with the calculations you've done is that it's simply the mass distribution which is causing the change in gravity. So again, we're looking at that differently and using the available